So here's the third exercise. This is the second one in, I think, part 7, solutions to that. So first we're looking for more examples of, just to make sure we understand the difference between these ideas. One would be a function that's Lipschitz but not bi-Lipschitz. So Lipschitz, remember, means the slopes are not too big, but bi-Lipschitz means the slopes are not too small. That's pretty easy to come up with something. So for example, y equals sine x. Sine x. Okay. Slopes definitely don't ever get big, but they get small. They go to 0 multiple times. So basically anything with a critical point is not going to be something we want when we are thinking about this as the condition we want. So how about locally bi-Lipschitz, but not bi-Lipschitz? Okay, so here we want that if we fix any little neighborhood, we can bound the slopes away from 0. But if we go globally, the slopes go closer and closer and closer and closer to 0. So, for example, the Gaussian, y equals minus x squared. I guess I was going to put over 2. Doesn't really matter. That's a standard normalization. Or y equals 1 over 1 plus x squared. That's called the Cauchy distribution in statistics. Any kind of hump like this, where the slopes definitely never getting big, okay? And if you look at any particular x naught, and you look near that, then yeah, the slopes are small, but you can find some c prime so that the secant slopes are bigger than the c prime. But if you take the x naught and you walk that out either direction towards infinity, that c prime is going to have to go to 0. Ooh, there's a c prime there. Okay, so that's a good example of locally bi-Lipschitz but not bi-Lipschitz. Okay, again, we really care more about the local thing because we're talking about local analysis and a local theorem right here. Okay, so yeah, this is from an earlier video, junk. Okay, so then a couple of easy implications. If f is bi-Lipschitz, and we'll do the global version first, even though that's not what we're really interested in, then f is 1-to-1. Okay. This is definitely, you should stop the video and really try to do this yourself because it's not super hard. Because we know that f of x1 minus f of x2, that's greater than or equal to c prime x1 minus x2. So if the outputs are equal, okay, then that's 0 and that's 0, and therefore x1 equals x2. It's that simple. Okay. So just a little more intricate, and not much, is if, this is what we really want for our purposes, if f is locally bi-Lipschitz, then it's locally 1-to-1. And the local inverse has good properties. Okay, well, let's just say it's locally 1-to-1. Well, this is just the local version of this theorem. Okay, we know that near, well, let's say for every x naught, there is a neighborhood v of x naught with f restricted to v, honest to God, bi-Lipschitz. Okay, and now just use this theorem, then it's definitely going to be 1-to-1 on v. Okay, so really we're just going to work with this function from now on. Okay, so f restricted to v. Okay, so now what is its inverse going to be? Okay, so that does have an inverse since it's 1-to-1. So that's f restricted to v inverse. Now, one of the subtle points that I talk about repeatedly in the main videos is that we haven't guaranteed that f of v is any kind of nice set, and that is really the most subtle point of the whole proof of the inverse function theorem for my money. But let's just say, okay, whatever that image was, it's going to be the domain of the inverse function. It goes back to the domain that we had for f. And the claim is that this is bi-Lipschitz. Okay, so it's in the same kind of good class. And that's not hard. We just write it down. The main thing is that we're going to start out with some things in the domain of G. Okay, well, those are, by definition, those are the image of two unique inputs to F. These live x1 and x2 are in V. Okay, and so let's just write down what the bi-Lipschitz condition says about f of x1 and f of x2, and that's automatically going to give us something about the y's and the g's. Okay, it's kind of a warm-up for some of the other calculations in the main videos. Okay, okay, so we know the bi-Lipschitz condition on f is that the variation in the output is bounded between two different constants times the variation in the input. Okay, so let's just translate that into the y's. These are y's, and these are g of y's. So g. Okay, and then this is another g of y1 minus g of y2. Okay, but now just like take this inequality for example. Just divide, c is a positive constant. It's definitely not 0, and we can definitely divide by it. Just divide it by c, and you put a 1 over c here. That's exactly the bi part of the Lipschitz condition. Notice this is the Lipschitz part, where the slope of the it came from the slopes of f not being too large. That implies the slopes of g are not too small, because we just get a 1 over c here when that goes away. Okay, and this is saying that these guys are bigger than 1 over c. So the 1 over the c prime for the g is 1 over c for the f. Similarly, if we just focus on this part, bring the 1 over c prime here, that says that the variation in g is not too big, and so that's the Lipschitz part coming from the bi-Lipschitz part of the f function. And we're done. This is a great example of pretty straightforward proof. And I think that was all I wanted to show for this.